Imagine the first ice crystal touching your skin. For the North American wood frog, this isn't the beginning of the end. It's a trigger for a radical biological cascade. This single point of contact sends a hormonal signal screaming through its body to its liver. The liver, a massive organ in this frog, begins a process of explosive glycogenolysis, frantically converting stored glycogen into glucose. Within minutes, its blood sugar levels skyrocket to concentrations that would be fatally toxic to a human, reaching over 200 times the normal level. This isn't just antifreeze, it's a cryoprotectant. The goal isn't just to lower water's freezing point, but to fundamentally alter the liquid state within its body to protect what matters most. As ice begins to form in the frog's body cavity, outside of its cells, it creates an osmotic imbalance. The water outside is now purer ice, so the remaining liquid is saltier. In response, water is actively pulled out from within the cells, flowing through specialized protein channels called aquaporins. The cells intentionally dehydrate, shrinking and concentrating their internal contents into a thick, viscous syrup. This syrupy state doesn't freeze with damaging, sharp crystals. Instead, it undergoes a process called vitrification, becoming a glass-like solid. The frog doesn't prevent freezing. It meticulously controls where the ice forms, sacrificing its extracellular spaces to save its cellular machinery from being shredded. But even controlled ice growth can be dangerous. Large crystals can crush organs and rupture tissues. To manage this, the frog's blood contains specialized anti-freeze proteins, or AFPs. These proteins don't work like the ethylene glycol in your car's radiator. They don't significantly lower the freezing temperature. Instead, they perform a far more delicate task. They are ice-binding proteins. At a molecular level, they seek out and physically attach themselves to the surface of nascent ice crystals. By binding to the crystal lattice, they act like guards, preventing more water molecules from joining and stopping the crystal from growing larger. This ensures that only small, harmless microcrystals can form, a phenomenon known as thermal hysteresis, keeping the ice manageable. Up to 70% of the water in the frog's body can become ice. During this time, it is clinically dead. Its heart stops beating entirely. Its lungs cease to function. There is no measurable brainwave activity. It is a solid, inanimate object. So how does it come back? The thaw is not a gentle awakening. It's a sequential reboot of a biological machine. The heart's own pacemaker, the sinoatrial node, is one of the first components to become viable, requiring minimal oxygen to restart. It begins to beat, pushing the incredibly sugar-rich blood through the still slushy veins. This vital fluid acts as both fuel and a thawing agent, jump-starting circulation, which then reanimates the lungs, and finally, the brain. Within a few hours of thawing, the frog simply hops away, having survived a state that we don't even have a perfect word for.
Monotony has grown fast. Nearly 2,700 people have watched in the last few weeks, yet less than 0.03% are subscribed. It would mean a lot if you joined by hitting subscribe. And again, thanks for watching.